Our next Runge-Kutta method is called the midpoint method. So here we have the generic Runge-Kutta methods. For the midpoint method, A2 equals 1 is chosen. A2 equal 1 would mean that A1 is a 0. And if A2 is a 1, that means P1 is equal to 1/2. And it means QII is also equal to 1/2. So those are the four values of our parameters in the Runge-Kutta method, called the midpoint method. And we end up getting this. yi plus 1 is equal to yi plus k2 times h. Now you might think, well, why do I even need k1? It doesn't show up anywhere here, but remember that k2 is a function of k1. It requires k1. So k1 is the same as before. k2 is simply going to be f of xi plus 1/2 h, comma, yi plus 1/2 k1 times h. So this is our formula to find the next y value at the next time interval. yi plus 1 is yi plus f of this times h. And what are we taking it, just in case you can't read it? xi plus 1/2 h, comma, yi plus f of xi yi times h. And then everything here multiplied by h again. Okay, same example. So the top looks the same. Here, the formula that we just went over, yi plus 1 is yi plus k2 times h. That's the midpoint formula. k1 and k2 are defined right there. So I equals 0. We start off exactly the same way. x0 is 0, y0 is 5. That's just because of this, our initial conditions. So k1, it's exactly the same as last time. Plug 0 and 5 in here, and you're going to get a 1. K2 is a little different. Here's the formula for K2. I plugged in the numbers, and you end up getting f of 0.75, comma 5.75. And think about what this is. This is 0.75 is only half of a step size. So take half of the step size. This is our estimate of the y value at half of that step size. And compute the slope using that formula. And that's the slope we use to predict from yi to yi plus 1. So K2 is equal to negative 0.8829. Okay, so that means that y1, which is y0 plus k2h, would be equal to 5 plus negative 0.8829 times h, which is 1.5. And that means that y1 is equal to 3.676. And that's our estimate for y at 1.5. And I'll go ahead and write it down, even though we know this. x1 is x0 plus 1.5, which is just 1.5. Okay, let's go to time or step size. Step I equals 1. Well, we have x1 equal 1.5, and we have y1 equal to what we just computed, 3.676. And now we'll compute K1 and K2 in a similar fashion. K1, which is f of x1 y1 is equal to f of 1.5, 3.676. So we're plugging these two numbers into this function right here, giving us 3e to the negative 1.5 minus 0.4 times y, which is 3.676. And we get that k1 is negative 0.8009. And now we'll do k2, which is equal to f of x1 plus 1/2 h, comma, y1 plus 1/2 k1h. And that is equal to, I'm going to skip one algebra step, and I'm going to go straight to saying that x1, which is 1.5 plus 1/2 h, gives us 2.25, and y1 plus 1/2 k1h is 3.075. And if you take those two numbers, 2.25 for x, 3.075 for y, plugging it in, you get negative 0.9138. So finally, we need to compute y2. y2 is, of course, our estimate of y at time 3, because it's our 0, 1st, 2nd step, taking us out 3, going 1/2 at a time, 1.5 at a time. That's equal to y1 plus k2h. So this is equal to 3.676 plus negative 0.9138 times 1.5. And that is 2.304. So this is approximately, this is our estimate for y at time 3, 2.304. And of course, x2 would be equal to 3. x0 is 0, x1 is 1.5, x2 would be 3.0. And this tells us that our true absolute relative error is equal to, if you remember, 2.763 is the correct number. So this one doesn't look as good as last time, using Hoyne's method or Hume's method. This error pretty significant, 16.57%. So for this example, Hoyne's method worked much better than did the midpoint method.